Last time I was explaining to you the hack I did in SCANC to get the synchronization right, or the phase relation right, between the horizontal and vertical counters, the shift register and the address counters of Cavia. It was so much of a hack that I didn't even want to try and explain to you why it worked. So that was done in the spirit of do as I say, don't do as I do, which is a motto valid for my other series on YouTube, the Pimp My 8 series. But then I thought, for building Cerberus, I set out to do something that was that should be didactical, clean computer architecture, clean and comprehensible design. So I thought, no, hacks would not do. So I decided to go back and do that the right way this time around, without funny delay lines, without the hack job that I hinted at previous time. So bear with me, I will explain to you now what is the right way to do it, and it so happens it's also a way that works, and works in a more stable way than the hack I did last time. In order for us to know how we have to schedule things, let's just remind ourselves again very briefly of everything that has to happen within one Cavia clock cycle, within one of these periods. Cavia has to present an address to the video memory, which in turn has to reply with a character token, which then is presented to the address bus of the character memory, which then also has to reply with a character byte, which then has to be loaded into SCANC's shift register, such that this little bit of the corresponding byte is presented to the screen. All this has to happen within one Cavia clock cycle, each and every one of them. So how much time do we have to do this? Well, the pixel clock here runs at 25.175 megahertz. But we know that the Cavia clock should do 1/16th of that, as we've seen in previous episodes. So the frequency that Cavia has is actually 1.57 megahertz. That's the frequency with which Cavia runs. Now, how much time does that give us per period? Well, if we invert this, we find out that we have 636 nanoseconds for all this to happen. Now, is this little or is this enough? Taking into account that I am using EEPROMs now, which are fairly slow, access time of 150 nanoseconds, we know that this response here is 150 and this is also 150, so we have 300. Now, this is relatively fast in comparison, and so is this in comparison. All of this is relatively fast, so we should have more than enough time. And after we move to the dual-ported SRAMs for video memory and character memory instead of EEPROMs, we will have even more time because the SRAMs are a lot faster. Now, having said all this, we have to give ourselves as much of this time as possible. So from the moment Cavia puts an address in the video memory address bus to the moment that SCANC latches the corresponding byte into its shift register, we want that elapsed time to be as much as possible, as high a percentage as possible of this allotted time we have here. We don't want SCANC to latch a byte here immediately after Cavia puts an address there, because then we will not have time for all this to happen. We want this latching to happen as far away as possible from the moment the corresponding address is presented to the video memory. That's the trick. So here's how we do this. Remember, we are using a 4-bit counter as a clock generation state machine. In fact, this is a 16-state state machine. Now, these are the possible states we have. We have to decide now which action to take on each one of these states, if any action is to be taken at all. How do you go about it? I'll show you what the most reasonable didactical solution is. The moment we have the first pixel clock tick, the counter will count to 1. So state S0 will turn to 1. that's the moment we want to immediately latch whatever is available from the character memory. We want to latch that byte into the shift register. Immediately we latch that. Now, in order to give our system as much time as possible between the time that an address is presented to the video memory and a byte is latched into the shift register, the natural next thing to do immediately after we load the byte into the shift register and we secure that byte, the natural thing to do next is to do a Cavia clock tick, because then Cavia will present the next address to the video memory, and we will have all this time here before the system loops back to load then the next corresponding byte into the shift register. So that's what we want to do. Immediately after we load a byte from character memory, we want Cavia to get a clock tick. Now, the load has happened here. So in this cycle, the least significant bit of the byte that has been loaded into the shift register has been presented to the screen. Each bit has to be presented twice, like we discussed in previous episodes, and the second time happens here, during the Cavia clock tick. So two presentations have been made, so now we have to go to the next bit. In other words, we have to shift the contents of the shift register. And then the new bit is presented once here, and it will be presented here. So the next shift should happen there, and so on and so forth, always with an empty cycle in between, because remember, the shift register clock should be half of the pixel clock. And this is what you see here. The shift register clock will tick here for the load, it will tick here for one shift, and then 1, 2, 3, 4, 5, 6, 7, 8. And all bits will then be presented twice, because remember, although the last bit is loaded here, the thing loops back, and in this state, nothing happens. So that's the second presentation of the very last bit in the byte. And then what happens after that? We load the shift register with the next byte. And immediately after that, we tell Cavia, go for the next address of the video memory, because you will have all this time here while we are busy shifting the present byte before we load the next byte into the shift register. So this is how this thing is supposed to work. And note, there are no go states, no delay lines, which we simply use the states of this counter as a little state machine and clock divider. Clock divider because, for instance, if we take only one of these 16 states, we get the Cavia clock at 1/16th the frequency, and if we take only every second state of the 16, we get the shift register clock. So this counter is at the same time a clock generation circuit and a little state machine that does that. So let's formalize this. How do we get the logic to generate the Cavia clock tick? And of course the whole thing loops around. So how do we generate the logic for the Cavia clock tick? Well, the answer is pretty obvious. We want the Cavia clock tick to tick on this state in which S3 is 0, S2 is 0, S1 is 1, and S0 is 0. So what would be the hardware description syntax for that in the CUPL language that we've been using? It would be this: Cavia clock equals the inverse of S3, so when S3 is 0, this is a 1, and the inverse of S2, so when S2 is 0, this will be a 1, and S1, because remember, S1 has to be 1, and the inverse of S0, because we want this to be 1 when S0 is 0. So this equation here will be true on this point, at this point here, which is exactly what we want. Now let's go further. How about the shift register clock? Well, notice that the shift register clock only ticks when S0 is 1, and it always ticks when S0 is 1. So what's the shift register clock? It is simply I meant S0 instead of S1. The clock should tick every time that S0 is 1. and it should never tick when S0 is 0. So that's the couple language, shift register dot clock equals S0. When S0 is 1, the clock will tick, otherwise it will not tick. Now the final thing we need to check out is, okay, how do we write the logic for loading a new byte into the shift register? Well, notice that the load only happens here. Now this is S0, so this is already the shift register clock. The clock will do nothing when S0 is 0. It will only do something when S0 is 1. So we can ignore this part and only look at the next 3 states, the next 3 bits. A load is done only when S3 is 0, S2 is 0, and S1 is 0. So what would be the couple syntax for that? You're already familiar with that. Each flip-flop in the shift register has the extension .d, and these would be the inputs. So look at the syntax here. When this equation obtains, when it's 1, in other words, when S3, S2, and S1 are all 0, then we will load a new flipped around character byte into the flip-flop. Or when this condition here does not obtain, then we will plug the inputs in such a way that the shift register will shift. It will take the contents of the previous flip-flop to the left and load them into the flip-flop to the right. So this is the logic. It's pretty simple. Now notice that I'm using a longer equation here. Before I wanted to use caveat clock here just to simplify things. But I can't use it now because you see the equations are no longer the same. And the reason I had this hack I did last time was simply because I just wanted to use caveat clock here because I was lazy. But at the end of the day, it only complicated things, so it pays off to do things right. And this is the way to do things right. Now, a common mistake here could be the following. You might think, well, I want to know when I have to load a new byte into the shift register. I do it here at this state, so I might as well take all 4 bits instead of only S3, S2, and S1. I might take S0 as well, and then you would write an equation like this with S0 at the end instead of this without S0. Well, for one, you don't need this because the shift register will only do something on the shift register clock, and the clock is already S0, so of course S0 will always be 1 in that case. So you don't need to do that. But worse yet, if you did it, it would not work. And that's where you have to think about the physical implementation of it, not only at the level of logic abstraction. The physical implementation of something like this would be this. You would take 3 negated inputs and S0 not negated because you want it to be 1, and then you would AND them together, and this would be either 1 or 0 depending on the input values. And then you would say, well, I just put this whole thing here and it would work. Now, it wouldn't. Can you see why? Can you see why it wouldn't work? For the following reason. The flip-flop will latch its inputs on the clock tick. So as soon as S0 becomes 1, the flip-flop will latch, and it will either latch the top or the bottom. Here's the OR, depending on whether this term here is positive or negative. But you see that latching will happen when as soon as S0 becomes 1. Now, if you put this condition here, there, remember that's the implementation. So by the time S0 becomes 1 here, there will still be a gate propagation delay before the output becomes 1 there. By the time this output becomes 1, and then you would do a parallel load instead of a shift, by the time this happens, the input has already been latched, because the input will be latched as soon as S0 becomes 1, not as soon as this output is ready. So in fact, when you latch the input at S0, this will not yet be true. I mean, this will not yet be true. This term will not yet be true. Therefore, you will shift. even when you're supposed to load, you will shift. So you have a shift register that will shift everything always and never load anything, so you would get exactly 0 in the video output if you did that. So here's the new CUPL file with the resulting implementation. Notice first that there is no more go state. I've added 2 atmel property calls. I'm turning off a couple of things because I was getting low levels and some funny unstable behavior during reset. So I've turned off these 2 properties. You don't need to understand what this is. Now that's the equation for the caveat clock that we've just reviewed. It's right there in the new file. There is no more clock enable with that go state in the horizontal counter. Going down the file, that's the shift register clock, which is just state S0, and that's the logic for deciding when to parallel load a new byte into the shift register. As we've just discussed, the second term is negated because that's the shift, and the first term is not, that's the load. And this is the final prototype in all its glory. Kavya now has the proper breadboard adapter, so it's now sitting in a self-contained breadboard with all the components we need, including a little trim potentiometer that you saw down there. There's a little buffer as well. I'll explain all this in a second, but it's a self-contained breadboard. All the pieces are in there. It only receives power from the outside and produces a video signal that also happens to be quite perfect. I changed the television settings for it to display the original 3x4 format instead of a stretched out 16:9. Alright, here's the prototype's final version. We have Kavya in there, in a little breadboard adapter, SCANC in there, also a somewhat larger adapter that's double EEPROM playing the role of video memory containing the character token codes. And this is the character memory containing the bitmaps of the character set. Now the general structure is what I've explained before in a previous episode. I will go over it very briefly. There is only one input to this circuit, and that's power. It only needs power. It has its own onboard oscillator, a 25.175 MHz oscillator, and it also has one output, which is the VGA signal that goes there. So it's an entirely autonomous circuit. Instead of the double EEPROMs, the final version of CERBERUS will have 2 dual-ported memories here, which means that the VGA circuitry can ignore what's happening on the other side of the dual-ported memories here. So that's why it's a completely autonomous system. When you turn on the computer, this kicks in, it does its own thing in a loop, and it will only stop when you turn the computer off. So roughly what happens is the following. Here is the oscillator that produces the original 25 odd megahertz signal. That's the output. It goes through this red wire into this buffer, which is a 74 HC244 buffer. It has 8 buffers in it. It goes in there and then it comes out, let me see, it comes out here. And through this green wire here to the back, it provides a pixel clock input to SCANC. Once SCANC has the pixel clock, it generates the Kavya clock, which is 1/16 of the pixel clock for Kavya, and the original signal comes out of SCANC here, behind, over here, through this white wire here, and then it passes through the buffer as well to get a little bit more drive, and it goes through this green wire here to the back of Kavya, and that provides the Kavya clock. With that clock, Kavya will just scan through all the character tokens in the token memory, line by line, 16 times per line. Each time an address is provided to the video memory here, a token code will come out through these white wires here to the character memory, and those provide the 8 most significant bits of the character address. Another 3 signals, 3 bits here in the green, also go to the character memory, and they provide the three lowest, least significant bits of the character address here. Then a byte is produced corresponding to a piece of the character's bitmap, and it goes through these wires into SCANC, and it's loaded in a shift register here in SCANC, and then SCANC will shift them out one by one, bit by bit, through this orange line here, which then goes through the buffer as well to get a little bit more drive, comes out here through this red wire, and then goes through this amplifying transistor, which is to provide even more oomph, more drive to the signal, because my experience has been that it's difficult to drive this connector, the VGA cable, and my monitor, so you need a lot of buffering there. That's why I'm buffering the signal twice. Now the vertical and horizontal sync code are in these two, sync pulses are in these two orange wires. They come in here, they are also buffered, and then they go out through this yellow wires there to the VGA cable. There is also a little potentiometer here which allows us to adjust the brightness of the image, and that pretty much completes it. This is a simple analog circuit. The signal to be boosted comes through this red wire into the base of this transistor. On the collector of the transistor there is a connection through this little jumper here, orange jumper, straight to the 5-volt power rail. There are two decoupling capacitors in there, and this resistor is connected from the emitter to ground. I've chosen a 75 ohm resistor here in order to do some impedance matching or impedance matching with the monitor, which is spec'd at 75 ohm, and that reduces the rippling, makes the signal a little more stable. And then the video signal is finally collected from the emitter of this transistor on top of this resistor here, and that goes through a trim potentiometer and then into this green wire here that goes all the way there to the connector, and that's the green signal. Now blue and red are not connected. I found that I get better, sharper image if I don't connect these at all, even better if I don't ground them at all, because there's some circuitry in the television that detects when there's no signal there, and then the equivalent circuitry in the TV probably is just shut down, and we get a sharper image that way. This is pretty much it, and it's working pretty nicely. Let's have a look at the signals, particularly the green color signal that's produced by SCANC. It comes here into this orange wire here. So if we probe the signal, the way it comes out of SCANC, you see it's 1, 2, 3, around 4 volts, quite a bit of rippling. But it is a digital signal if you see at this scale. So this is roughly at 4 volts, and it goes through the buffer and comes out on this side, and now we have closer to 5 volts, and then it goes through this buffer. It comes into the buffer here through the base, which is the same signal you just saw, around 4.5, 4.8 volts, and on the emitter is the output, and notice it's back to 4 volts. That gives you an idea what the load is here. It's pretty severe load. It's difficult to drive this connector, the VGA cable and everything. So even with buffering twice, including with a high current amplifying transistor, the signal still goes down to 4 volts. Now in principle, for a regular VGA monitor, this is 4 volts is more than enough. A regular VGA monitor expects a peak-to-peak amplitude of 0.7 volts only. So why am I trying to get even more than 4 volts? Because for some reason my TV, which also has a VGA input, seems to expect TTL level signals, so peak-to-peak of 5 volts. But these 4 volts will do. Another interesting signal to measure, if I can show you, is the clock input to Cavia, and there you can see how useful the buffering is. This is a 0, so 1, 2, 3, 4, 5 volts. So this signal is nicely buffered. It's going over 5 volts on the top ripple. Before it is buffered, it comes in here, and you see that's only 4 volts. And then it would have to travel through a long wire to Cavia with only 4 volts amplitude. That's not a good idea. So the buffering really helps. Remember, this part of the circuit here operates at over 25 megahertz. This is, it starts being testy for a little breadboard prototype. Normally 8-bit computers don't operate at more than 3.5 megahertz in the case of a Z80, or even less than 2 megahertz in the case of a 6502, which does more per clock cycle. So a breadboard prototype is perfectly alright. But because this is a VGA circuit, there is a high-speed component going on here. This Cavia clock is less than that. It's a little over 1.5 megahertz, but even then the wire is long, so this green wire here is long, so it's nice to buffer the signal just before the wire so it goes through it with the appropriate strength.
And this concludes our development of the video circuitry of Cerberus. I hope you've found it informative. From the next episode on, we will begin to tackle the I/O control, the input-output control of Cerberus. As usual, when you're building a new computer, you build it from the outside in, so you always can see and control the guts of the computer, which will be the last step we take. Join me then for the next episode, whenever I'm up to completing that. Take care. Thanks for watching.